It turns out, the universe doesn't need to invent monsters to be terrifying. Its sheer scale, its crushing emptiness, is humbling enough. For decades, astronomers looked to Alpha Centauri with a sense of hopeful familiarity. At just 4.3 light-years away, it's the star system next door. It's so close that if the distance from the Earth to the Sun were a single inch, Alpha Centauri would be just over 4 miles away. For all of history, it's been a beacon in our southern sky, a constant, luminous friend. Science fiction has long imagined it as our first interstellar destination, the obvious next step for humanity. The system has not one, but 2 stars, very much like our own sun, Alpha Centauri A and B, locked in a graceful 80-year orbital dance. A third, more distant and dim companion, the red dwarf Proxima Centauri, is already known to have planets. Logic, probability, our best models, everything screamed that Alpha Centauri A and B should have worlds of their own. And yet, for a century of looking, we found nothing. A baffling, improbable void. The system was too bright, too close, and its twin suns created too much glare and interference. It was a cosmic paradox. The easiest place to look was the hardest place to see. But then came the James Webb Space Telescope, a machine built not just to see, but to see the impossible. It was designed to capture the faint, ancient light of the universe's first galaxies. So, pointing it at Alpha Centauri, the brightest and nearest stellar target, was an act of audacious, almost reckless ambition. The light was so intense it threatened to blind the very sensors trying to read it. And yet, they did it. And what they found wasn't a warning. It wasn't a message. It was a single, impossibly faint pinprick of light. A ghost on the lens. To really get why searching Alpha Centauri is both so tempting and so maddeningly difficult, you have to understand the system itself. It's a place of profound complexity that masquerades as a simple, sun-like neighbor. Through a small telescope, Alpha Centauri looks like one brilliant star, the third brightest in our night sky. But with better instruments, that single point of light splits into 2. Alpha Centauri A and Alpha Centauri B. Star A is a G-type star, same as our sun, just a bit bigger and brighter. Star B is a K-type, a little smaller, cooler, and more orange, but still perfectly capable of hosting planets. These 2 stars are locked in a celestial ballet, orbiting each other every 80 years. Their distance from each other swings wildly, from about the distance to Saturn at their closest, to further than Neptune at their farthest. This constant gravitational tug-of-war has huge implications for any planets trying to form there. The environment isn't calm and predictable like our solar system. It's chaotic. For decades, many astronomers thought this chaos was a deal-breaker. Models suggested that gravity would either fling any forming planets into deep space, or send them spiraling into one of the stars. A stable orbit in the habitable zone, where liquid water could exist, seemed almost impossible. And then there's the third wheel, Proxima Centauri. It's a tiny, dim, red dwarf. In fact, even though it's the actual closest star to us, you can't see it with the naked eye. Proxima orbits its 2 bigger siblings at a vast distance, a journey that takes it well over 500,000 years. For a long time, Proxima was just a cosmic afterthought. But in 2016, that all changed. Astronomers announced the discovery of Proxima Centauri b, an Earth-sized planet orbiting right in the middle of the red dwarf's habitable zone. More planets were later suspected around this tiny star. This was a seismic shock. If the smallest, dimmest star in the system could host a rocky world, the odds of finding planets around the two much more stable, sun-like stars suddenly skyrocketed. The hunt was back on, but the fundamental problem remained. Alpha Centauri A and B were just too bright. Searching for a planet next to them is like trying to spot a firefly hovering next to a colossal searchlight from miles away. The star's glare completely washes out the faint reflected light of any world. The very air we breathe distorts the starlight. The two stars are so close together in the sky that their light overlaps and interferes, creating a confusing mess in any telescope image. For ground-based telescopes, it was a near impossible task. This is why our closest neighbor has remained a frustrating puzzle. We knew something should be there, but we just couldn't see it. It was like living next door to a house, hearing faint sounds from inside, but being blinded every time you tried to peer through the brightly lit windows. What astronomers needed was a tool that could not only stare into that glare, but surgically block it out. They needed an eye in the sky, a machine that could perform a feat of cosmic surgery. They needed the James Webb Space Telescope, and they needed to push it to its absolute breaking point. To understand how Webb even attempted to solve this paradox, you have to remember it was never really built for this. JWST was designed as a time machine. Its massive, gold-coated mirror was made to capture faint, ancient light from the dawn of creation. Its instruments were cooled to just a few degrees above absolute zero to be hypersensitive to the infrared heat of distant, alien worlds. It was optimized for the dim and distant universe. Pointing Webb at Alpha Centauri was the opposite of its primary mission. It was like using a microphone designed to hear a pin drop and placing it next to a jet engine. The sheer brightness of Alpha Centauri A was a danger to Webb's delicate detectors. The team had to write custom protocols just for this target, carefully calculating exposure times to avoid permanently damaging the multi-billion-dollar instrument. It was a high-risk, high-reward move. The key was one of Webb's instruments, MIRI, the mid-infrared instrument. MIRI is Webb's eye for the colder, dustier universe. But it has a secret weapon, a piece of tech absolutely crucial for this ghost hunt, a coronagraph. A coronagraph is basically a tiny, precision-engineered mask inside the telescope that creates an artificial eclipse. Just as our moon can block the sun's disk to reveal its faint corona, MIRI's coronagraph can be positioned with microscopic accuracy to block the overwhelming light from a star. The team used a specific mask designed to block light at a wavelength of 15.5 microns, a sweet spot where a gas giant planet like Jupiter or Saturn would be expected to glow with its own internal heat. But the challenge was way more complex than just sliding a mask into place. There were 4 huge obstacles that made this one of the most difficult observations Webb had ever attempted. First, no coronagraph is perfect. As light bends around the mask's edge, it creates a complex pattern of rings and spokes, artifacts that can easily be mistaken for a planet. Second, Alpha Centauri isn't one star, it's 2. The coronagraph could block Alpha Centauri A, but its brilliant companion, Alpha Centauri B, would still be blazing away nearby, scattering its own light all over the detector. There's no way to block 2 separate bright stars at once. Third, the stars are moving targets. Because Alpha Centauri is so close, it appears to move across our sky much faster than distant stars. Webb had to track this movement with unheard-of precision, keeping the star perfectly centered on a mask just a few pixels wide for the entire observation. And fourth, there's the problem of cosmic imposters. When Webb stares at Alpha Centauri, it's looking through a crowded field of countless other stars and distant galaxies. Any faint dot could just be a background galaxy billions of light-years away. To overcome all this, the science team devised an ingenious observation strategy. It wasn't enough to just take one picture. They pointed Webb not only at Alpha Centauri A, but also at a completely different, unrelated star of similar brightness. This reference star gave them a clean template of Webb's own instrumental noise. By carefully subtracting this reference image from the Alpha Centauri image, they could, in theory, remove all the artifacts, leaving behind only the light that was unique to the Alpha Centauri system, and just maybe, the light of a planet. It was a data processing nightmare, a surgical procedure performed with algorithms on terabytes of data. They were pushing the telescope and the very techniques of astronomy into uncharted territory, building a ghost trap for something they weren't even sure was there. In August of 2024, the command was sent. 1 billion miles from Earth, the James Webb Space Telescope swiveled its golden eye toward our nearest neighbor. For hours, it locked on to Alpha Centauri A as its MIRI instrument meticulously executed the complex dance. The coronagraph slid into place, the detectors gathered photons, and the raw data began its long journey home. On the ground, the team held its breath. The initial images were a mess. Just as predicted, the glare from Alpha Centauri A created a brilliant halo, and splashed across the frame was the overwhelming, scattered light from Alpha Centauri B. It looked like a hopeless, chaotic flood of photons. This was where the real work, the digital archaeology, began. First, they digitally subtracted the light from the companion star, Alpha Centauri B. A huge amount of the contaminating glare vanished. Next, they subtracted the instrumental artifacts using the data from their reference star. Layer by layer, like peeling an impossibly complex digital onion, they stripped away the known sources of noise. And then they saw it. As the final layers were peeled back, a single faint point of light remained, a dot. It was located about twice the distance from its star as Earth is from the Sun, and it was incredibly faint, over 10,000 times dimmer than the star itself. The team designated it S1. The excitement was electric, but so was the caution. This was exactly the kind of discovery that makes careers, but also the kind that can evaporate under scrutiny. The first question was brutal. Is it real? Could it be a glitch? A hot pixel on the detector? A cosmic ray that hit at just the right moment? Or was it one of those background galaxies, a cosmic imposter? The team ran a battery of tests. The object's shape matched the profile of a real light source seen through Webb's optics. It wasn't a sharp, unnatural glitch. It wasn't in their reference star data, so it wasn't an instrumental artifact. And they combed through catalogs. No known galaxy or star was at that exact location. After weeks of cross-checking, they had ruled out every error they could think of. The evidence pointed strongly in one direction. S1 was a genuine object, physically associated with Alpha Centauri A. They had found a planet candidate. The implications were staggering. If confirmed, S1 would be a Saturn-mass gas giant. It would be the closest exoplanet to Earth ever to be directly imaged. Its position swept through the outer edge of Alpha Centauri A's habitable zone. And while a gas giant can't host life as we know it, this opened up a tantalizing possibility. Moons. Could a Pandora-like moon, warmed by its sun and the gravitational tug of its parent planet, be orbiting S1? The speculation was wild, but for the first time, it was grounded in something they could see. What's more, the very existence of a gas giant here challenged our models of planet formation. The chaotic gravity was supposed to make this impossible. If S1 was real, it meant planets are more resilient than we ever gave them credit for. But science demands more than a single glimpse. To confirm a planet, you need to see it move. You need to track its orbit. The team was granted special observing time on Webb for a follow-up. In February and April of 2025, Webb once again turned its golden eye to Alpha Centauri A, ready to confirm our newest, nearest planetary neighbor. The data came down. The team ran the same painstaking analysis. They cleaned the images, peeled back the layers of noise, and stared at the spot where S1 should have been. And there was nothing. The planet was gone. The faint dot that had appeared so clearly in August 2024 had completely vanished. The ghost in the machine had disappeared. The empty images from early 2025 sent a wave of confusion and disappointment through the team. The immediate conclusion was that S1 had been a fluke. Maybe a random asteroid in our own solar system photobombed the original image. Maybe it was a temporary cloud of dust from a collision. Or worse, maybe it was some subtle, misunderstood glitch in the instrument that had fooled them all. The most exciting exoplanet discovery in years was on the verge of being retracted. But then, Aniket Sanghi, a Caltech PhD student on the team, asked a different question. A question that turned the entire mystery on its head. He asked, what if the planet isn't gone? What if it's just hiding? This question launched one of the most intense computational investigations in recent memory. The team didn't give up on S1. Instead, they decided to model its behavior, combining the 2024 Webb data with another tantalizing clue. A faint hint of a planet candidate called C1 that had been spotted on the opposite side of the star by a different telescope back in 2019. Could S1 and C1 be the same object, seen at two different points in its orbit? They ran millions of computer simulations. They created a virtual Alpha Centauri system and populated it with potential planets, giving them every possible orbit that could connect the 2019 detection with the 2024 detection. Then, for each of these millions of stable orbits, they asked the computer a simple question. Where would the planet have been during the follow-up observations in early 2025? The result was the stunning twist in the story. The models showed that for 52% of all the stable orbits that fit the data, the planet would have been completely invisible to Webb during the follow-up attempts. In more than half of the plausible scenarios, the planet, following its path, would have moved into a position where it was either directly behind the star or so close to it that its light was completely lost in the glare. This was the revelation. The non-detection wasn't evidence against the planet. It was perfectly consistent with it. The ghost hadn't vanished because it wasn't real. It had vanished because it was playing hide and seek. And in early 2025, it was hiding. The lack of a signal, which at first felt like a failure, had become a new piece of corroborating evidence. From these simulations, a clearer picture of this phantom world began to emerge. S1 is likely a gas giant with a mass similar to Saturn on an elliptical orbit that takes it around its star roughly every 2 years. Its path takes it sweeping through the habitable zone, making it the first directly imaged planet candidate within the habitable zone of a sun-like star. But the story isn't over. A candidate, no matter how strong, isn't a confirmation. The team has made a prediction. Based on their models, they know when the ghost should reappear. The simulations predict the planet should once again become visible to Webb in August of 2026, 2 years after its initial discovery. A proposal has already been submitted to use Webb at that exact time to look again. If they see that faint dot of light, right where their models say it should be, the candidate will become a confirmed planet, Alpha Centauri AC. It will be the culmination of a decades-long hunt, a testament to ingenuity and relentless scientific detective work. The story of S1 is more than just a thrilling cosmic detective story. It represents a fundamental shift in our ability to explore the worlds in our own neighborhood. For years, the best ways to find exoplanets have been indirect. We look for the tiny dip in a star's light as a planet passes in front, or the slight wobble in a star's position from a planet's gravitational tug. Both methods are incredibly powerful, but they don't show us the planet itself, and both are extremely difficult to use in a binary system like Alpha Centauri. The direct imaging of S1, even as a candidate, heralds the start of a new era. An era where we don't just infer that planets exist. We take their pictures. We see them as distinct points of light. This allows us to not only confirm they exist, but to study their light directly, to analyze their atmospheres, and maybe even search for the chemical fingerprints of life. And the hunt at Alpha Centauri is far from over. Webb's discovery has galvanized a new generation of missions. One of the most exciting is a small space telescope called Ptolemy, set to launch around 2027. Instead of trying to block the starlight, Ptolemy will use a special lens to spread it out into a complex, flower-like pattern. By precisely measuring tiny changes in this pattern, scientists can detect the stellar wobble caused by an orbiting planet with unprecedented accuracy. It's a mission custom-built to find Earth-sized planets in the habitable zones of Alpha Centauri A and B. The scientific community is no longer asking if there are planets there, but what kind of planets they are. S1 has reshaped our expectations. We once imagined Alpha Centauri might be a mirror of our solar system. Now, we're faced with something more dynamic, a system with a large sweeping gas giant that would have profoundly influenced any smaller, rocky worlds. Does a planet like S1 act as a guardian, protecting inner planets from deadly comets? Or is it a bully, its gravity having already ejected any potential Earth-like worlds from the system long ago? These are the questions that will drive the next decade of research. And they are questions we can now begin to answer. The viral story of a terrifying warning from Alpha Centauri was fiction, but it was born from a very real human desire to know if we are alone. The truth, as it so often is more subtle and ultimately more profound. There was no alien message, but the universe was speaking to us. It was telling us that the worlds we seek may not be where or what we expect. It was telling us that discovery is a process of patience, curiosity, and learning to see through the glare. The story of S1 is a perfect example of how science really works. It's a journey filled with mystery, frustration, and breathtaking moments of revelation. We went from a sensational story of a silenced warning to the intricate real-life hunt for a planetary ghost. And honestly, a Saturn-mass planet playing hide-and-seek in a chaotic binary system is a far better story. It's a story that's still being written, with the next chapter scheduled for August 2026. What do you think Webb will find? Will CS1 reappear, finally taking its place as the closest imaged exoplanet? Or will the system hold on to its secrets a little longer? Let me know your thoughts in the comments. The universe is full of these mysteries. If you want to keep exploring the greatest cosmic detective stories of our time, make sure to subscribe. Every new observation brings us one step closer to answering that ultimate question: are we alone?